Good afternoon, everyone. Thank you, Mr. Chairman. Before I start my presentation, I'd like to acknowledge the contribution of my co-authors, my PhD students, Mr. Lee and Mr. Nasrullah, and then Ms. Wang, which is also a PhD student but is a visiting scholar from China. I am the director of the Laboratory for ND and Structural Monitoring at the University of Pittsburgh, and the project that I'm going to present today is mainly funded by the Pennsylvania Department of Transportation and partially by the U.S. National Science Foundation. Briefly, the outline of the presentation, we'll start with the background, and then I will present some of the results associated with the numerical and the experimental results that we achieved in our lab. And then, of course, I will end the presentation with the conclusions and then some time for questions and discussion. So what we are presenting here, what we propose is a new method, a new NDE method, a non-destructive examination method based on highly nonlinear solitary ways to quantify the strength of concrete. Solitary waves are basically compact mechanical waves that can propagate, form and travel in only particular type of materials. Like granular materials, layered materials, fibrous materials, and so on. Simplest shape of the material is a material that is made by a chain of spherical particles. Here the solitary wave is induced by impacting the chain with a strike, and then after the impact, basically a compact wave propagates through this one-dimensional chain. So why solitary waves? Solitary waves have special properties. And one of the most important is that they are tunable, which means that we can control the wave properties by choosing the characteristics of the nonlinear medium, in this case the chain of particles. Just an example, in terms of properties, I mean here the amplitude, the bandwidth, and the speed. So, for instance, we can increase the amplitude and the speed of the wave by increasing the elastic properties of the particles or by decreasing the size of the particles. So we don't need any electronic, any function generators or stuff like that. We can just tune the property of the chain. So the research hypothesis for this particular project is the following. Let's assume that we have a chain on top of the concrete that we want to inspect. The chain is impacted by a striker, the stress wave propagates, it reaches the interface, and then a part of the energy is reflected back. So the research hypothesis here, first of all, this is, let's say, an ideal shape of the incident wave that goes toward the sample and then the reflected wave. So the hypothesis here is that the time of flight, which is basically the time interval between these two peaks, and the amplitude ratio, which is the amplitude between the reflected and the incident wave, is strictly related to the mechanical properties of the concrete in this case. So just to show you an example but applied to a beam made of steel, here is a beam of steel in which the Young modulus is 100 gigapascal, the Young modulus or the Young modulus is 220 gigapascal. These are numerical methods and numerical results that we obtained in our lab well before this project. And as you can see, the reflected wave, which in this case we call primary solitary wave, has some change which is not visible, both in the time of flight and the amplitude. But in this case, there is the formation of a secondary solitary wave, and this secondary solitary wave is generated by the local vibration of the sample. And in this case, the characteristics of the wave, it's strongly dependent on the Young modulus. So So basically we investigate the same thing on the concrete. What we investigate is the hypothesis that if we test concrete we can achieve this kind of performance in terms of any approach. So what we did? First of all, we build our sensors, and I know that this might look bulky, but this is an initial study, an initial stage. So we started with the simplest approach. So we designed, assembled 4 transducers to try to increase, to have more transducers to assess also the repeatability of the setup. The transducers consist of chain of particles made of stainless steel, and on top of this chain you can see here there are electromagnets that basically lift and release the top particle of the chain, which in this case is going to act as a striker. And then the electromagnet is controlled by a data acquisition system such that all the experiments can run basically forever. We just need to push a button and then we can test for hours without any problem. Last but not least, in order to sense the waves, we have solenoids and permanent magnet in order to realize what are called magnetostrictive sensors. So these are the elements that actually physically measure the stress wave that propagates through the chain. And actually you see here at the bottom one of the concrete slabs that we tested. And actually here is a close-up view of the concrete slab that actually we borrowed from a colleague of mine who casted these slabs months before the experiments. And again, for the sake of repeatability, we tested 8 slabs to check the repeatability of our setup. And for each transducer and for each slab, we collected 100 measurements. Which means that each measurement, basically we lift the striker dropped, the wave propagated, reflected back, and we collected the signal, we stored the signal for post-processing, and we repeated this 100 times, but automatically. So overall the measurement took probably 2 minutes, 3 minutes, depending on how much we set the repetition rate of the striker. Meantime, we got the results from our colleagues in terms of the ultimate strength and the modulus of the concrete that were obtained using a conventional STM standard test. So here are the experimental results. This is the average of 100 measurements collected by the 4 sensors from one single slab. Here is the incident wave, this is the reflected wave, and then we have a small secondary solitary wave which indicates that at the interface the bottom particle of the chain vibrates slightly. And you can see here, you can appreciate here the fact that the time waveforms are quite repeatable. So the 4 sensors are repeatable. The results refer to a slab, and each time waveform represented here is the average of the 100 time waveforms. So we consider in this presentation I'm going to present the results relative to the time of flight, relative to the primary and the secondary solitary waves, which again are indicated here with this light. So here are the results. The time of flight of the primary solitary wave with respect to the slab number. Let's focus first on the first slab. Here are the 4 results from the 4 sensors. The results, I think they are very close together, despite this is an experiment, so it's not a numerical model. And here there are barely visible the standard deviation of the experiment. So here is the average value, and the vertical bars represent the 2 sigma interval of the experiment. So the chain, the experiment is quite, the transducer is quite repeatable. And here is the result from the second slab, and we have good agreement. And this is the result for all 8 slabs. So it seems that despite we are dealing with concrete, which not as homogeneous as steel, I believe that this is a very good repeatability in terms of experimental results. When we are dealing with the secondary solitary wave, we have more scatter. In this case, I think that the problem, we believe that the problem, if it's a problem, the scattering of the data, is that the signal-to-noise ratio is quite small. How we compare, or how we then calculate the Young modulus? We modeled, we developed a numerical model that, for the sake of time, I'm not presenting here, but we can discuss during the coffee break or tomorrow when I can eventually bring with me my laptop. But basically, from this numerical model, from the experimental data, then we can back calculate the Young modulus of the samples. And we have some outliers, but by removing the outliers, the Young modulus, the average of the 6 left slabs is in the order of 30.9. It's not very clear on the screen. Yeah, it's 30.8. And the result from the conventional test, the destructive test obtained months earlier, have a minimum maximum between 29.9 and 30.7. So we are pretty close to the destructive to the values obtained with the destructive test. So in conclusion, we presented here a novel non-destructive evaluation method to infer the strength of concrete. We found a promising agreement between the results with our method and the values that usual engineers obtain using a conventional destructive methods. We developed, but we did not show here, the analytical model to predict the response of the solitary waves, and then to predict, to back calculate the Young modulus and eventually the Poisson's ratio of the sample. However, this is an initial study. Concrete is not again an homogeneous material, so definitely more experiments are warranted to prove this technology even more. Thank you for your attention, and questions are welcome. Thanks.